Let's start again by looking at where we left off in the pre-class lecture. We talked about the approximation-generalization trade-off as being another name for the bias-variance trade-off. The key idea here is that we want to minimize our test cost. We want to be able to approximate the target function well on new unseen data. We saw when we use a larger hypothesis space, or a more complex one, because of the richness of the hypothesis class, we have a much better capability of approximating F on the training data. However, having a more complex hypothesis set also means that generalization is harder. When we move to a smaller, less complex hypothesis set, we have a better chance of generalizing out of our sample data set. This is because the different types of plausible hypotheses are quite distinct from each other, and it's easy to use the training data set to localize which one would be better. Ideally, of course, we would like a hypothesis set that just includes the target function, just one of a kind. Of course, that's almost impossible to wish for, and so there's always a trade-off about deciding to use a larger, more expressive hypothesis set or one that's less complex. So we're going to quantify this trade-off between the test cost, which is ultimately what we want to optimize. We're going to look at how well the hypothesis set that we choose best approximates F overall on the training data, and how well we can find the correct optimal set of parameters theta when we are faced with the problem of generalizing on the target set. Now, this analysis applies to real value targets, and to make the mathematical notation easier, it uses squared error. It doesn't directly apply to binary classification as we've done so in parts of our course, but there's an equivalent binary version that you can derive through the lens of another form of this trade-off analysis, which is more common to SVM theory, which we'll touch upon later on in the course. This is through the lens of VC analysis, or Vapnik-Chervonenkis theory, which looks at a particular set of points to do its analysis rather than the hypothesis set overall. To derive the analysis of bias variance as we've done in the pre-lecture notebook, we're going to start by understanding what it means to minimize the cost function on the test set. Now, whatever this means, it has to be dependent on a specific hypothesis, and that hypothesis needs to be generated with respect to a particular choice of the data set. What we mean by this is that the data set describes exactly which hypothesis we're going to pick. In many of the learning algorithms that we have seen, it's a deterministic process that results from the particular instances that are available in the training data set. And to calculate the expected test cost, we have to go through the expected values of our instances with respect to their probability distribution over the input data points. So here we're taking the particular data points, calculating what the hypothesis would generate, subtracting by what the actual value is, and then squaring this result. So this is again the squared error term. Now this is with respect just to one particular data set, but we need to be able to generalize what we mean by the test error over all possible data sets. So we're going to generalize what we mean by D and look at how the test cost varies with respect to our expected data sets. We can write this out. Just plugging in the previous formula that we have up here. Since both of the expectations are over non-negative values, we can swap the integrands. It won't matter which order that we're going to take them in, and it's more convenient for us to look at the dependencies on the data set, the inner terms first, and then we'll write the outer term here. For now, we're going to focus on this inner term, and then later we're going to come back and deal with the outer parts. And so we've written out this step for you here, just in case you'd like it more cleanly annotated with some colors to help you look at the bracketing and the terminology. So now we'd just like to focus on this particular term that we showed from the last slide. And if you look at this particular thing, it's very interesting because we can define something that's correlated with it, which is the average hypothesis H bar. What do we mean by H bar being an average hypothesis? We mean over any particular set of points, let's say we have k points in total, we can draw any number of data sets of that finite value. So for example, let's set k equals to 5, then I'm going to draw from my probability distribution of my x values a sample of size 5, another sample of size 5, keep on drawing many samples of size 5, okay, and then dividing through, and each time we have this data set, we're going to create a hypothesis using machine learning to get the optimal weights given that particular training data set. And then what we're going to do is we're going to average them. We're going to take all of the different hypotheses that are generated. Let's say we drew k as k tends to infinity number of data sets. We're just going to average all of the hypotheses together to get an average hypothesis, right? So it's basically a sort of voting. An analogous way to think about it is that each of these k hypotheses are different students trying to learn a concept. So for example, let's say that different primary school students are trying to learn the idea of subtraction, and each of the primary school students is exposed to a different data set of subtraction problems with answers. When they're faced with a new problem, we ask all of the different learners, we ask all of the different primary students what their answer is, and we average all of those answers together to come up with the average hypothesis. Now, sometimes the average hypothesis is actually within the class itself. So for example, when you're thinking about H0, which is the type of function where you only have a single intercept, no slope, then if we average all of the different votes for different y-intercepts, would still be a y-intercept of some value. This is also the case of H1, where you have different lines with different slopes, and averaging all of them together still yields us a line parameterized by theta 1 and theta 0. So let's see how using H bar will help us with our analysis of bias variance. I'm going to focus in on this term at the beginning again. And let's go to write it out on the next line. And I'm just going to write the hypothesis that we're generating with respect to the learner minus the actual value. I'm going to take that and square it, and we have the identical formulas on the previous line. What I want to do now is employ H bar somewhere. So what I'm going to do is subtract it in one place and add it in another place. This is obviously legal because I'm not doing anything. I'm just adding a net zero to the equation. But the important part with that is that I can get to do some association of this. And when I reassociate the terms, I can write a second version of the equation. where I take the first term and the last term. So I'll take 2 copies of this, 2 copies of the last term, and I'll have that out. Now, where did the cross terms go? Actually, we need another half line for this because we're not done. We have the cross terms here, which has 2 of the first and the second, right? So you get something like the second term that I've copied in, and we have 2 copies of them. And what can we notice about this bottom term? So interestingly, when we just focus on this first term here, we'll see that it's over the entire, is the expected value over all 3 terms. The 2 copies of the first term, the 2 copies of the last term, and our 2 cross terms. And if we look at this particular expression here, what is its value? Well, while we're looking over all of the different data sets, right, we're looking at the expected data set, and we're integrating over all of these to get the expected value. Well, what does that mean? We define the expected value of the hypothesis as h bar, right? So this value and this value are actually identical because of the way we defined what the average hypothesis said. It was basically the hypothesis that we had over all of the possible expected data sets. So this term is going to go away. It's going to be a 0 because the 2 terms are identical. So 2 times 0 times a constant, because actually this is going to integrate out to be a constant as well because it doesn't depend on the data set. So it's going to be some constant c is going to be equal to 0. So happily, all my cross terms go away. Zap. And I'll end up with this expression, just copying our first terms that we had before. Where this second term, as I said before in the black, is a constant. So that's why we can take it out of the expected value. And so you can see this all nicely written out here. Hopefully it's understandable after I've narrated it a little bit. And so we've ended up with these 2 terms that you see here. We have a first term that's dependent on the actual data set that's being picked, and another term which is only dependent on the hypothesis class. So hopefully you've been following along, and now we want you to guess. Spend a minute here and think about which one is the bias and which one is the variance. So you have 2 options. Maybe 1 is the bias and 2 is the variance? Or is it the other way around? 1 is the variance and 2 is the bias. Hopefully it's clear that the second term is looking at something that's systematic about the type of hypotheses that could be generated from the hypothesis set and doesn't depend on the particular draw of the data set. So that must be something intrinsic to the hypothesis set, which would be its bias. And the first one is dependent on the particular data set that's being drawn, so that must be the variance. Now we have to go back and understand what we're going to do when we were talking about the expected values of x. We left that to be done after we did the work on looking at the dependency on an expected data set. In fact, we can just write this out pretty simply as having these 2 terms of bias and variance with respect to x. And we're just going to term them in general as bias and variance over the entire data set. What this is saying is the test cost can be exactly divided into two separate parts. One to look at the representational bias of the hypothesis set that's chosen and the variance that's due to the particular sample that's been taken. And we can really think of this as a trade-off that we'd like to be able to optimize. When we have a very small hypothesis set, let's say just the size of 1, probably it doesn't represent our target function very well because it's a very impoverished representation. So there'll be a lot of bias error represented by the distance between this particular hypothesis set and the target function. However, in the small hypothesis set, where there's only one hypothesis, we don't have any variance because basically it's insensitive to any data that's passed to it. Whatever data is passed, I'm still going to return this one hypothesis because it's the only one that I have to give you. On the other hand, when h is really large, we have a very good chance of encompassing the target function. So here, we can see from all these blue dots that the target function of a red square is actually within the capability of our hypothesis set to model. But the problem is we have to actually find a target function, and that depends on the specific draws of the data sets D. When we draw a particular data set, given the probability distribution of P, we're going to get one of the data sets that allow us to find and localize within the hypothesis set a bit, and hopefully we'll pick out something close to the target function. If I happen to sample a data set that encompasses different types of hypotheses, I'll average this point, this point, this point, this point, and this point, and get my average H bar as something close to the centroid of this point, which won't be close to the target function. So we can think of it really as a trade-off. On one hand, we could have a very small hypothesis set and have only bias error, potentially very high, and on the other side, we could represent the target function fairly well, meaning that there's low bias, but finding the exact hypothesis that's optimal would be difficult, and we would have high variance. Depending on the representation of the hypothesis set, our average hypothesis could be around here, being closer to modeling well, or maybe it could be down here. Again, depending on where we set our hypothesis class. So it really is a trade-off. We're deciding how much bias to accept the modeling error and how much variance to accept the localization error. Take a few moments to try to relate this to the worked example that you saw as illustrated in the pre-notebook. These all come together as part of a coherent example of both the theory and the practicality of the bias-variance trade-off.